Yeah, so you've been really trying to narrow out on that particular type of problem.
Yes.
And how does that look like from a deep learning perspective? What type of problem is it from a deep learning perspective?
Right. So here comes a cool thing that I'm sure other people have thought about it, but I was sort of spellbound when I discovered it. I've always felt that graphs were very fun to work with. They're a fun data structure and there are neat algorithms for working with it. And it's also one of those problems, funny enough, that's very difficult to parallelize. Mm-hmm. All the algorithms for graphs are just, it's hard to split a graph in half and do the one half first. So we were working with graphs when we were in telecom. And we were like, okay, how can we apply AI here? And here's a fun intuition first. So convolutional networks are working on images, and images are just graphs where every node always has 8 neighbors, right? Mm-hmm. And then
6, or
isn't it 6 and then 2 on the side?
Yeah, true.
Yeah.
8. Okay.
But it's a graph, and then I'm like, okay, well, we know convolutions work, and then funny enough, after a couple of years, graph convolutional networks started being a thing, and they work precisely for the same reason that they work well on images, is because the locality thing applies just as well on graphs, and graph neural networks work really well. So we started playing around with those, and we wanted to try some simpler stuff first. And I discovered that word2vec worked really well on graphs.
What's this?
So there's this method called word2vec, an older language processing method that you feed it a sequence of words and it guesses what the next word is, basically. And I thought, well, that's sort of like a random walk on a graph. What if I feed it a set of nodes and I want to guess what the next logical step in the graph should be? And funny enough, word2vec was really good at that. It memorized the graph, and it figured out what the smart walks along that graph are. And obviously, it made an embedding in itself of the graph, the big graph into a tiny embedding in the network, and it became really good at walking across the graph. And now, do we know any other models that are really good at handling sequences? Right?
Now we get there, yeah?
Yeah, so that's where transformers come into the picture. And funny enough, transformers are really good on graphs, walking along graphs. And so there's a more advanced version of the traveling salesman.
Because I think this is super interesting discussion, of course, and understanding and how to generalize sequences such as text into graphs is very interesting. But how do you really do that? How do you sequence basically a graph into something that you can then apply transformers or word2vec to?
I don't think you sequence the graph as such. What happens is in the word2vec case, if you feed it a number of walks along the graph, it'll only make an embedding of the parts of the graph of the walks that you've fed it.
So basically you find a path. That's the sequence, right?
Yeah,
so you basically sample paths through the graph, and that becomes sequences in some way, right?
And so you can't solve all kinds of problems, or maybe you can. I haven't thought about it enough, but for the convnet, you can make sort of an autoencoder style where you have one network that goes in. Let's say you want to solve the optimal network flow problem. And so you have a network, an energy network, let's say.
I was thinking.
Right? And one of the machines breaks down, and you want to know, how is the energy going to be rerouted? Is that going to make back pressure? Is it going to break some component? That's an NP-hard problem to compute. You could have a graph convnet that is like an autoencoder and spits out a more optimal network flow, or perhaps a predicted network flow or something else like that. But that's not so much a sequence problem. A sequence problem, the kinds that we've been looking at are if in the case of telco, if a user is traveling along the highway, what is the most logical set of bounces along the towers? Because that's very stochastic. Like, you think you would connect to the best tower, but you don't. And so we wanted to make models that would guess what's the next tower that the person would probably connect to. And the fun thing is, what we've discovered is transformers can learn a lot more about the logic of the jumps between the sequences. So, for example, in the traveling salesman, the most optimal path that the traveling salesman would take is not necessarily a greedy approach, taking the shortest path and then the next shortest path. It might be something that looks less optimal, like you start with the node that's furthest away because the ones afterwards are shorter or something. And with transformers, you have attention. So the transformer will look at all the sequences it can take, and it'll say, I see that that's where I should be starting. And it can be really clever about things that are out of order and that kind of thing.
And for people that don't know the huge difference between word2vec kind of models and transformers, how would you describe transformers compared to word2vec?
I think for me, the two things that are interesting are the attention mechanisms that transformers have. So basically, you can think of an attention mechanism as a softmax that puts the focus on what part of the problem that the machine should be focusing on next.
And this could be a sequence of words, or it could be a sequence of nodes in some path.
Yes. One thing that I haven't really wrapped my head around yet is I saw a paper quite recently that showed this working very effectively on images as well. That you cut up the image and it outperforms ConvNet. That boggles my mind a little bit, but so the attention
sequence of pixels row by row, basically, right?
I think they tried using convolutions to bake down each quadrant in a picture into single vectors, but they found that they didn't even have to do that because the attention mechanism sort of figured that all out for it.
Exactly.
And so you have an attention mechanism, and what it does is, I think the nicest analogy is in language translation. I was fortunate when I was at Tele2. I was working on a what I thought was a pretty groundbreaking project, real-time translation of voice while you were on the call. We were going to connect it to the network, so you would dial, star blah blah, and it would translate you from Swedish to English or whatever in real time. And we were going to use Microsoft's API. And the fun part is when you're speaking in German, the translator has to wait until, has to place the verb at the end. So there's this huge delay when you're trying to speak German. And you'll notice that when you're in Skype or Teams and you turn on the auto subtitles, the German thing will wait and wait and wait, and boom, the verb comes at the end. Attention mechanisms let you sort of look at what's relevant in the sentence, and separate the order of things. So whereas old methods like recurrent neural networks would have to remember things for a really, really long time, a transformer can look at everything at once and just look at what's important in the moment instead of bringing along with it everything. This really long set of information. And that's probably why it works better, I think.
Yep.
And what was the difference to word2vec?
Word2vec is word2vec even recurrent? I don't know.
No, it's not. It's just a pair. Usually the skipgram is just a pair of nodes connected. So it's
so
predicting the next word you can think of, or a context of a word. Yeah. So it's extremely much more simplistic. It's like a single neural network compared to like millions of parameters in the original transformers.
So this is interesting. So this is interesting now. I guess you have started to talk to people in industry around that, and do they fundamentally understand the difference? This is a leading question, but do you have any anecdotes for us on like how do people experience you or this understanding that there is a different route down to this problem? It should be huge in the transport industry, in the logistics industry to start thinking about it.
I mean, even small logistics companies are delivering tens of thousands of packages per day that they need to optimize. So they all stand to benefit. But the really big ones in this country here, they have a turnaround in the tens of billions of crowns. So any 1 or 2 small % improvement, we're talking about hundreds of millions. In potential savings. I think that's a pretty compelling AI argument if we're talking about business cases. And so, I'll speak about this topic, and it's not like people haven't thought about this before. And you're very safe buying off-the-shelf products. But when it comes to it, and you need to explain what the difference is, and that it's an ocean of difference, it's very hard to quantify it. I've had a lot of problems where I run the neural network, and it goes boom, and it's done, right? 300 milliseconds. And I'm like, did you catch that? Yeah, no? Yeah, it was pretty uneventful. I don't know what else to say, but how long does it take you guys to run? And it's, we run it on a cluster of 5 machines for all night. And it's like, yeah, so is this useful? And they're like, I don't know. I'm not sure exactly what happened, but we have this other use case, and then it sort of dies there. Yeah, I think what we've found, and this applies to everything else, you need to have pie charts and dashboards and dots and moving stuff for it to work.
As a sales pitch.
As a sales pitch. The first gigs we did at my old company, we did this really cool stuff with Cloudera, and we connected it to Power BI, and connected it to Cortana. So you could say, "Hey Cortana, how many units have I sold?" And it would get it all the way back. So I was
Cortana is the voice assistant, basically.
Right, the voice assistant in Microsoft. And I was really proud of that whole thing. But the only thing that really stuck from that meeting was the voice activation. And it's the same thing here, where it's really tough to explain why, to big companies, why this is useful. To startups, it's different. So these little companies that live and die by the margins, they will take any small advantage they can. So that's where we've made more inroads than with the big traditional companies, where I think there's more to gain.
The real opportunity is there, but is it as simple, fast, and happy? Or is it uneducated, or is it too hard? I mean, the big company always, to have respect, when you come with change, it's painful for them like hell to change or to adopt and put things in production.
I think at a startup, you can go speak to a CTO, and the CTO will be both the person that understands the full tech stack, has a 20% stake in the company, and answers to the board of directors, and has a time, and has everything in one place. And you can say, I can do it in this time, it's this valuable, and you can have one conversation with one person that understands everything. At a big company, you have the CEO that reports to the board and is only really interested in making sure that they get their money, what do you call it? The yearly...
Year-on-year growth kind of thing.
Yeah, that kind of thing. Not necessarily reducing operational costs in the moment. They want to get their dividends, stock dividends. They want to make sure that the dividends are good this year. Yeah. So maybe even the CEO that answers to the stockholders might not necessarily be interested in making operations better. So you end up having like 5 people that you have to talk to. The CTO that understands the tech, somebody that's responsible for operations, somebody that's responsible for the profitability of the company. So obviously that's a harder sell and conversation than the startups.
Before we move away from the paper that you submitted, and I think it's a fun topic that we really didn't dig deep into sufficiently. So perhaps one question is basically, what's the difference between taking the approach that the paper takes and trying to find an approximate solution to TSP compared to using machine learning or deep learning for that?
Yeah. The paper and the mathematicians want to find an exact solution to the traveling salesman problem.
Yeah.
And there is a provable bound to how much time it can take in the worst case.
And it doesn't even found in this case, I guess, the optimal one. It's just some kind of close to the optimal one that it can guarantee to find, right?
Yes. Deep learning models are not guaranteed to find anything special. We can sort of run it many times and say most of the times it looks like it finds a good solution. And that's the same with all these physics approximators and everything else. There are many heuristic methods already, algorithmic heuristic methods for finding pretty good solutions to the traveling salesman problem. Methods like ant colony optimization, genetic algorithms, simulated annealing, which is an inside joke because it sounds so advanced, particle swarm optimization. All these methods are like gradient descent, I guess, that exists in machine learning. And they'll find a pretty good solution. The transformer, though, tends to beat those by quite a lot. It's both a lot faster and gets a better solution. But it doesn't find the optimal solution, ever, basically.
Probably not. But still, in the approach of what they take in the paper, trying to basically define an algorithm from a manual coding point of view almost, or mathematical point of view, compared to just throwing data to it and automating, I guess. Or would you say that that's basically the machine learning approach in trying to use data instead of manually coding it in some way? Or would that be a good way to describe it? Or how would you describe the difference of what the paper does and a transformer would do to try to solve the TSP problem?
All sort of complexity theory is in quantifying what each step of an algorithm does so that you can set a bound on what the worst runtime is. So it's really probabilistic, and you can set, you can give guarantees on how bad or good the solution from this is compared to the transformer method, which is very much reliant on the data that you give it. Coincidentally, I think the secret sauce that we have in how we've implemented the transformer is that.
So, by the way, you have like a prototype of using transformers for TSP?
Good. For sure. For vehicle routing. So TSP is just one person. And then there's the constrained vehicle routing problem, which is many trucks with many constraints, time windows for deliveries, how much packages you can fit in it. And we've made working prototypes that are very performant, very good. And what we're hoping to do this fall is sort of verify that it's useful. I think a lot of we've been speaking to companies that say, well, our biggest problem is that we only have 2 loading bays and there's always a queue. So, imagine we save each truck 15 minutes every hour. Yeah. And then they come back to the loading bay and they're in line for 2 hours. So we haven't saved anything. So the point now is to verify that this really does save time for real companies. So
just to understand, how did you actually build this transformer-based kind of route optimization problem? Did you collect data in the beginning somehow?
No.
Or
well, I'm not going to give away too much of the secret, but it's I can say all graphs are the same, really. So you don't need data from a specific graph.
Okay.
So the traveling salesman problem is generic enough that you can take data like road, how much traffic there is and other stuff, and that's useful. But the route finding intelligence is general purpose. So for that, you can use other learning approaches than training on data. So it's not a supervised approach that we've used.
Okay. So it's a self-supervised somehow, that you basically predict the next step in the graph somehow? Or?
Yes.
Yeah. Okay.
Super cool.
You're going to milk this one out?
Yes, I want to.
Call to me is always a self-supervised is the way to go.
We're going to make it all open source, and it's all in Julia, so ha.
I'll wait until I see that, but okay.
But
before we close that discussion, I think a lot of people don't understand really the difference between using machine learning or deep learning compared to like trying to manually program something.
Yeah.
And it would be fun. Okay, let me make a statement and see if you agree with it. So one, it's super hard to manually code and find like an optimal algorithm for doing whatever, including solving TSP or something else.
Yeah.
And then you can try to mathematically find some kind of bounds and do some guarantees on it. That can be useful, but usually it's kind of worst case analysis optimization that doesn't really speak about the real world and the average case analysis and the results. So in reality, perhaps you don't really need or have that much use for the worst case analysis that many of these papers focus on.
Sure.
Right?
Yeah.
And then the question becomes, okay, and given that if we were instead to care about like the average case analysis and the performance of that, then we need to find an algorithm that works really well for that. And then we can try to manually code it, or we can throw data at the problem and use some kind of model like word2vec or transformers. And that basically, would you say it's basically like automating, building the solution to find the route somehow? Or
yes. Well, so just with regards to the bounds of expert systems, if we call them that, that was something that bugged me a lot when I was working on operating systems. You would be making a memory allocator, and you had a choice. Either you could optimize for the worst case scenario and remove the latencies, or you could optimize for the type of memory workloads that people tend to use. And you might get these tail latencies that were really long, but on average, you would just be performing really well. And there is no solution one algorithm is good at one thing and another one is good at another thing. And it really bugged me that all the focus tends to be on the worst case.
Yeah. Especially in academia, right? Or
yes, it's always something, but 99% of the time it's something else. Yeah. And I like that about deep learning and training on data, or training on patterns, because it's pretty realistic, and I think we don't always know what contributes to the output as much as we think we know, and I trust the data.
Yeah. Can you share some kind of, if you have some initial like benchmark results comparing like word2vec to transformer model in terms of performance?
I mean, word2vec was basically struggling to do Dijkstra's algorithm. So it could find the shortest path sometimes, but it would never be able to do this. I mean, we have a transformer that does the constrained vehicle routing problem in one forward pass and gets to within 2% of optimal. Oh. I mean, and it trains in like a day.
Oh, really?
On a big workstation.
And that's like a smaller version of a transformer? Or
it's just a small transformer, but so we have these nice machines from HP that have like 90 gigs of GPU RAM, but I mean, this is stuff that a company can buy.
It's not the GPT-3 10 million times.
No, not quite there yet. No.
I'm biting my tongue again.
So the joke is, isn't this a GPT-3 problem we can fix?
It could be. Maybe I need to outsource it to OpenAI or something. Yeah.
But to be frank and not make people think that this is actually true, then of course your fine-tuned version of a transformer would outperform GPT-3 if you try to throw it anything in a zero-shot learning setting.
Yeah. By far.
So this thing is made only to solve this problem, and it's very tiny, and it's tiny because we know exactly what it's going to work with. Yeah. And it's not comparable.
But this conversation we also had a little bit like very, very interesting about how to be successful in understanding where to go with new products and toolings. And I think Luca said it, what's the opportunity for Europe? As one of our guests here, Luca from Peltoria, right? Yeah. And we talked about this, it's in the tooling. And then, okay, well, what type of tooling are we talking about then? And then we're joking about the GPT-3. But it comes down to, if we figure out, that we want to be world dominant, but in a quite concrete niche or a quite concrete algorithm, that seems to be not a bad idea. Because all of a sudden you can now come back to the whole idea that how do you do something with AI that is kind of cost efficient and simple and can even be where the complexity in the end, if it's one-dimensional problem, you can kind of hide that complexity in the end quite nicely. Think product, which if you do this too broad stuff, it's just going to be... So I think this is cool. I think this is almost like a concrete example of what we're talking about, the technology. Yeah. We're using transformer approaches, but here we see now very concrete, very like this.
And you just need some web developers to make some nice UIs.
That's what I'm saying. That's.
I need to learn some JavaScript. I've been putting it off for all these
thought that out.
Do some React and then you're set to go.
Do some React. Yeah.